In this video, we're going to talk about measurements and how they interface with both units and uncertainty. To start us off, we need to define these two terms of different types of observation data. Observation data can either be quantitative or qualitative. Quantitative referring to something that is numerical, answering the question of how many or how much. So I could say this cart is moving at 15 meters per second. A qualitative measurement is a description that does not use any numbers. So if I were testing a chemical reaction and I mix two chemicals together and I notice that it's producing a gas, I might say that this is bubbling. That is not a quantitative observation, but it is still an important observation. In this particular video, though, we're going to focus on quantitative and really answer this question of how can you quantify a measurement? How can you describe something in a way that somebody else can understand how big or how much? To do that, we need units. If I were to say to someone that I weigh 20, that doesn't mean a whole lot because there is no unit assigned to it. It'd be a very confusing statement otherwise. So we have 7 fundamental SI units. SI in this case stands for System International. And these 7 fundamental units are the building blocks for every other unit that we're going to see throughout the course of physics. You need to know these 7. Length is measured in meters. Mass is measured in kilograms. This is the only one that is not a base unit. Kilogram is much more convenient in an equation than grams would be. Time is measured in seconds. Electric current is amperes. Temperature is Kelvin. You might be familiar with using Celsius in other science classes. Kelvin is more closely connected with what a molecule is actually doing, and that is more useful to us in the world of physics. Amount of substance is measured in moles, and luminous intensity is measured in candela. Of these, the top 6 will be pretty commonplace in IB physics. We won't really hit this last one, but the top 6 will be pretty much all over the place. Now, these units, while they feel very official and something like we've always had, they are still arbitrary. They are a human construct just to be able to communicate an understanding and quantify a measurement. The meter used to be defined as the length of a pendulum that would swing half of its maximum in 1 second. It was redefined then to be the length 10 millionth the distance between the North Pole and the equator, redefined again several times to be the length of a physical object that was stored in the basement somewhere in Paris. And then finally, in the 1980s, it was redefined once again, one final time, to be the length that light travels in a certain period of time. This is what we are talking about when we say 1 meter. Now, every time we are measuring in meters, we are measuring it against this reference point. Now, when you do that, you are naturally going to come across 2 terms that are important to describe your measurement. That is precision and accuracy. Precision is thought of, one way to think of it is the degree of exactness in a measurement. This can also be thought of as the repeatability of that measurement. So you can think of it in terms of how fine of detail your tool is able to give you, your instrumental precision. Or if you make one measurement 5 times, uh, you're not looking for a major spread or bouncing around of that data. You want something that is very repeatable. Accuracy is how close we are to that standard that we are referencing. So if my standard was I had an object that I knew was exactly 100 grams, I put it on a balance and it gave me 99.998 grams. That's really darn close to 100. We will say that that is accurate. And it has really high precision with a tiny number or a tiny increment size. So that's both precise and accurate. We expect maybe that last digit to bounce around, but if that's all that's bouncing, this is a very precise measurement. That spread is very small. Here I have 93 grams for that same object. That is not close to the standard of 100, so it is not accurate and it's not precise because it's measuring to the nearest gram. We have no decimal places there. This next one is precise, and it's got the thousandth of a gram, but you'll notice 87 grams is not very close to our standard. Maybe something was incorrectly set up in this balance. It might have been taired incorrectly. Somebody hit the 0 button at the wrong time, and it has an offset of 13 grams. This last one here, it measures exactly 100 grams, which is kind of what we would expect, but the precision, it goes to the nearest gram. So we would say that that is accurate, but it's not that precise. Here's an example IB question or two. Which of the following is a valid statement? A measurement that is not precise can be accurate. A measurement that is precise is always accurate. A measurement that is not precise will always be inaccurate, and repeated measurements will always increase accuracy and precision. Now, of these, we saw an example of one of them. We saw this one where it measured exactly 100 grams. That was accurate, but it was not precise. So, of these, A is our best answer. For number two here, an archer aims 5 arrows at the center of a target. The arrow strikes the target as shown here. Which of the following describes the aim of the archer? While they were aiming at the center, they did not hit the center. They are not accurate. This is getting at that repeatability definition. It's hitting the same spot over and over. That is precise, but it's not accurate. Now, when we talk about uncertainty, this is our way of quantifying the precision. So every digital tool has some built-in rounding. If some electronic balance says 100 grams, that doesn't mean that it's exactly 100 grams. That would have rounded 99.6 up to 100. It would have rounded 100.4 down to 100. So we need some plus or minus value to give us a range that we are confident contains the actual measurement on it. So if it says 100 grams, the way that we are going to define uncertainty for a digital tool like this is plus or minus the smallest division. This is going up and down by grams to the nearest gram. So we will say our uncertainty is to the nearest gram. So 100 plus or minus point, or 100 plus or minus 1 gram. This next value, 99.998 grams, our smallest division is a thousandth of a gram. So our uncertainty is plus or minus 0.001 grams because that is that smallest increment. Now we can report these given any measurements that we have. This balance here is showing 90.0 kilograms. That then can be thought of as 90.0 plus or minus 0.1. Here I've got 19.99 volts. That is 19.99 plus or minus 0.01. Now these uncertainty values, again, it's just looking at the smallest division and plus or minus that. Now I want to point out this is a pretty generous uncertainty. Technically, this 90.0 could be 90.05 and down or 89.95 and up. This uncertainty is giving us 89.9 to 90.1. So that's a little bit wider range, but that's okay. We'd rather be generous with that uncertainty than stingy. So this uncertainty, what we are talking about, actually has a name. We call it absolute uncertainty. So if I give you a measurement 2.0 plus or minus 0.3 grams, 0.3 grams, that's the absolute. That's the absolute uncertainty that we have. It will always have a unit that matches the measurement. Fractional uncertainty is taking that uncertainty and dividing it by the measurement. So the absolute divided by the measurement gives us 0.3 over 2 or 0.15. Percent uncertainty then takes that fractional and multiplies it by 100. So we would get 15%. Now, why that might be useful to you, if I said 2.0 plus or minus 15%, it gives you a sense of how big of a deal that uncertainty actually is. Plus or minus 15% is fairly substantial. If this were 200 grams, plus or minus 0.3 grams, that would now be 0.15% uncertainty. It's a much tighter range and a much more reasonable value based on the whole, what your measurement is. So if we look at this example of a voltmeter, the absolute uncertainty is based on the smallest division. In this case, we have 0.385 volts. The smallest division is a thousandth of a volt. So my absolute uncertainty is 0.385 plus or minus 0.001 volts. Fractional takes that 0.001, divides it by the measurement, so we get 0.0026. Notice that this has no unit or symbol. We just divided volts by volts. It's a unitless number. Now we can turn that into percentage, multiply by 100, and get 0.26%. So we could report that as 0.385 plus or minus 0.26%. Now, an example IB question, looking at the same idea, a current in a resistor is measured as 2.00 amps plus or minus 0.02 amps. Which of the following correctly identifies the absolute and percentage uncertainty in the current? Well, the absolute is given to us. It's right here. It's 0.02 amps. So that narrows our list down. Our percent then we take that 0.02 divided by 2 times 100, and we get 1%. So we're looking at A in this example. All right, what if it's analog? So all the examples that we saw here were digital measurements. Analog has slightly different rules. Analog tools require that you measure to one decimal beyond the increment, and the uncertainty is half the increment size. So an example of an analog tool would be a ruler. Here's a really basic ruler. If I wanted to measure this note card, this ruler is pretty bad, very low precision. It has an increment size of 10 centimeters, we'll say. Now, my best I can do, this goes up by tens place. So the best I can do is to measure to the ones place, to the nearest centimeter. We're going to call that, I don't know, 6, 7. We'll say 7. And then our uncertainty is half the increment size. The increment size is 10. So our uncertainty is plus or minus 5. Now, I want to point out this is a pretty generous range. That 7 plus or minus 5 says that we know the true value is somewhere between 2 and 12. Now we know for sure it's between 2 and 12. This will get tighter as we get to be a better ruler. So if I change my ruler to this, okay, I see it's not 7, it's somewhere between 6 and 7. So let's call that 6.7. Now my increment size is 1. Half of that size is 0.5. So we'll say 6.7 plus or minus 0.5 centimeters. Now we'll do it one more time. This has now an increment size of 0.1. So we can go to the nearest hundredths place. Let's say 6.72 plus or minus half the increment size is 0.05 centimeters. So you'll notice as my ruler got more precise, my uncertainty got smaller. That range got a little tighter. Now, the last thing I want to point out in this video is we can also use significant digits to basically show a level of precision. So here we have two basic rules. To figure out how many significant digits something has, we will count the numbers. And then the funny business is when you get zeros going on. Zeros only count if there's a decimal and they are to the right of other non-zero numbers. It's easiest to see an example. This first one, 3.45 centimeters. All of them are significant. That is 3. There are no zeros. It's pretty easy. Or 22 or 226.5 centimeters. No zeros. All of them are significant. It's 4. Now we've got 2.50. There is a decimal, and the 0 is to the right of other numbers. So we will say that that is 3. The 0 counts. Whereas here, 0.025, those zeros show up to the left of that decimal, so they do not count. We have two significant digits here. Now, this next one is where it gets a little tricky. 12,060 meters. This first 0 is trapped between, but this last one is to the right. So because there is no decimal showing that that is significant, we are only going to count the first 4 and say that there are 4 sig figs. Now, this next one, most of these zeros are not significant. They are to the left of the numbers, but the one to the right counts. We'll call that 3. Here I've got 25.0. That 0 counts. It's 3. 25,000 millimeters. There is no decimal. These zeros to the right do not count because of that. So we would just count that as 2. And then this last one is actually the same value as this one above it. But because it's written in scientific notation, we are able to see a 0 after a decimal. That shows that there's actually more significant figures here. There are 3. Now, I don't want you to get too worried about this. For an IB exam, you are going to get all the points if you round it to at least 1 sig fig away from where it should be. My recommendation is round all answers to 3 sig figs. It's very rare that you're going to see something with less than 2 or more than 5 or more than 4. So you're going to most likely get it right if you are rounding to a normal person amount. Here's an example of somebody that didn't round it to a normal person amount. Over the summer, there was a Major League Baseball all-star game, which they had a home run derby that they tied number of home runs, and it went to whoever had the longest home run. And Major League Baseball tweeted that the winner won by less than 0.1 feet, and then published a value comparing the two to 10 decimal places. That In an example of too many significant figures, there is no way that their measurement was that precise. Somebody actually did the math and found that that was around a picometer in size, which then puts it in the range of an oxygen molecule, an oxygen atom, which is tiny and not something that was really possible. So in this video, you should be able to describe the difference between quantitative and qualitative, name the 7 fundamental SI units, define precision versus accuracy and give examples of both, calculate absolute, fractional, and percent uncertainty for digital and analog measurements, and be able to determine the number of significant digits in a measurement.